Alrighty, so hi everyone. My name is Christine Ramdin. I'm a junior faculty instructor at Rutgers New Jersey Medical School Department of Emergency Medicine. I have a PhD in biomedical informatics. I've been with the department for the last 6 years, and I've done a lot of work. I assist my department with stats as well as conduct my own research in substance use and addiction. I was fortunate enough to initiate the series with Lane as well as Lynn. So thank you guys for, helping put all this together. I think hopefully this would be a great preface to, help empower our emergency medicine physicians at the junior faculty level, as well as residents to embark on some of their own stats, which will help, publish some of those probably lagging research papers quicker and, so they feel more confident going into it. So you'll find that a lot of times, unless you're publishing a huge, groundbreaking randomized control trial, a lot of the stats that you use in some of your studies and what you may have seen published are actually pretty basic, and still they get published. So oftentimes studies are published not because of the fancy stats used, but because of the novelty of the study idea. That being said, today I'm going to almost provide what one would consider almost like a refresher on basic stats or descriptive statistics, which is as important as any other type of more complicated stats because it will set the groundwork for all of the future work that we will do throughout the series, as well as what you will do in the future. So just a quick comment, I have no disclosures to make, except for the fact that many of the images used in the PowerPoint that I did not take snapshots of came from the internet. But if you would like to know at any point where I got any other pictures in particular, I'd be more happy to share those links with you after the recording. So in general, and we have to start with this as this will dictate kind of very much all the tests you use in the future. It'll help you make that decision. So there's 3 types of variables or 3 types of data overarching that you will encounter. There's scalar data, scalar data, which is continuous data, nominal data, and ordinal data. Continuous data or scalar data is typically like your height, weight, distance, time, or any number that can take on decimal points as well. Categorical data or nominal data, as in the name, we talk about categories here. So this can be like gender, color, race, and gender, we have the categories of male and female or non-binary. Color, we can have red, blue, pink, purple, whatever. Race, we have several races: Asian, African, Caucasian, etc. So nominal or categorical data are data that take on, can be categorized into different categories. And lastly, we have ordinal data. Ordinal data is like our Likert scale data. Scale data, like from, I don't need to use the word scale there, but like when you think of Likert scale, you think of data that is usually numbered from 1 through 5. Data that does not take on any decimal points, and they have discrete measures, right? So the 1 on the Likert scale means not likely at all, if you're looking at it from that perspective, and then 5 will mean very likely. So Likert scale data is a type of ordinal data. So again, this is very important as this will help you to determine what statistical test to use based on your data types. Because usually you cannot use the same type of statistical test for nominal or categorical data to compare between groups as you would use continuous data. And that will become more clear as we move on throughout this PowerPoint and in future sessions. So in general, there are 3 types of descriptive statistics, broadly speaking. To categorize them, they are central tendency, variability, and frequency distribution. And I'm sure you all have seen this before, but this is just to kind of help, put it together for you. So when we talk about central tendency of your data, that's like, your first instinct, right? When you're looking at a data set you have, if it's a data set of heights, your first instinct might be like, I don't know what to do with this. Maybe I'm going to sort it and then kind of look for the mean, median, and mode. Those are like the most basic things you can think of. And just to skip forward a slide to like kind of more demonstrate a little bit more about central tendency. When we talk about central tendency, automatically sometimes a picture comes to your head about, the normally distributed curve. And in a normally distributed curve, when your data is normally distributed, the mean, median, and mode, we kind of all know it's generally the same. So in general, we don't live in a perfect world. The data may be close to the mean, median, mode may be close, but not the same. But a lot of the times, if it's close, your data can be considered normally distributed. To the left and right, you see you can also describe your data with mean, median, and mode, but the data distribution or the curves are shaped differently. These are for skewed data sets. And noticeably for skewed data sets, like to the left of the screen, you notice that the data distribution is leftly skewed because the data points start falling to the left. And to the right, the curve is skewed to the right as most of the data points start falling to the right. The mean, median, and mode are not at the center. They're not equal for each of these distributions. They take on different values. So skewness becomes very important later in this PowerPoint slide because it also helps you determine what statistical tests to use. But just by looking at this data distribution, just like plotting it on a graph, a lot of information can be obtained and it could help you determine what steps to take next. So at this point, before I start blabbering more, are there any questions?
And I'll just interject, like, please put questions in the chat. I am monitoring them so that we can kind of hit Christine with them as we go and make sure that we're keeping everybody on track with what she's explaining.
Thanks, Lane. So that was a little bit about central tendency, and we'll see how this comes more into the bigger picture. The other, usually with central tendency, we notice also in papers that variability, different measures of variability are reported, right? Like you never see that, someone just reports the mean alone. They usually report the mean with the standard deviation. Why? Because it helps the reader get a more larger visualization of what the data distribution looks like, right? Like if we have a lot of data points and we report our mean and the standard deviation is small, that probably means it's simply an indicator that we have a lot of data points. So there's probably not a lot of variability. Like if, the data set's smaller, the sample is like 25 or something, you might find that the standard deviation is a little bit larger. So variability is important to report because it gives the reader a better sense of what that data distribution looks like. QR is usually reported with medians. Now, later we'll talk about when to report medians versus means when we're publishing a paper. We also have seen standard error reported as well as percentile. So these are all examples of data variability that are usually reported with measures of central tendency. Last but not least, we have frequency distribution, which is like count data. And as complicated as that sounds, it's really not that complicated. Just think about it like this. We have a bag of marbles, a bag of colored marbles, and there's several different colors inside, and we want to know what is the frequency of each type of color marble in that bag. So that's simply count data. We're counting the frequency, the number of different types of colors of marbles in that bag, right? I included this PubMed link here because it's actually really useful to review these different types of concepts that I've talked about. On your own time, it's a very simple read. So if anyone wants me to share that link with them later, I'm more than happy to as well. Let's see. Okay, so a lot of these data distribution things and statistics can usually easily be done in Excel. So right here, I kind of put the commands in Excel, but what I'm gonna do right now is I'm gonna stop sharing the screen and share an Excel screen so you guys can see how this works in real time. So we're going to share Excel, share. So I'm gonna also show you guys a cute, neat little trick. So as you see, I have no play data here, but I'm about to generate random data really quick. So there's an Excel command called rand between. So I'm going to show you how that's used right now. So in Excel, I'm going to type equals rand, R-A-N-D, between, B-E-T. And what that essentially will do is I specify a range of numbers and randomly give me a number within that range. So I'm going to tell it to give me a random number between 1 and 100. So that populates the first cell. And what I'm going to do is probably a lot of you know, I'm going to drag it down so it gives me more random data in a lot of cells. So here I have a random data set. And now we're going to try to do some basic stats on it. So I'm going to simply go into a brand new cell. I'm going to type in, say if I want to find the mean of the data set or the average, I'm going to type in equals average, and I'm going to select the cell range for which my data is located, and I'm going to hit enter. That's how you find the average of that data set. Simple as that. And now if you're worried, you don't want to tamper with this data set, but you want to do something else with it, I'm just going to copy and paste it into a brand new set of cells. Now we're going to calculate median in the same way. So I'm going to hit equal median, and then I open parentheses, I select my data set, and then I'm going to hit enter. And that's the median of the data set. So is there a command for equals mode? There is a command for mode. 1 second. So we're going to do mode as well. I'm going to copy, paste. It might have just changed my data set when I copied and pasted, but that's okay. That's completely fine. But be mindful when you're working with your own data, it's not going to change like that because you're not going to be randomly generating data like I am. It's going to be standard data that you have, so you will not run into that problem. However, words of advice, in case you're scared of losing data or whatnot, it may make sense to copy and paste your data into a couple different tabs. So while you're data manipulating, if you mess up on one page, you can always go to the next page. So I'm going to type in equals mode, and it returns the mode of the data. So one thing I want to quickly point out, if you notice, if we just not think about the mode for a second and pretend it was close, you notice the mean and the median to this data set unintentionally are pretty close. Now, while they're not exact, later I'll show you a tool that, essentially, since they're close enough, this will probably be considered normally distributed data. But there is a formal test we can use to test for that, which I'll show you later. But it's good to just observe and get that idea, like, in your head, this might be normally distributed. It may be okay to use a parametric test over a non-parametric test. Lane, would you like to say something?
Yeah, so that actually leads exactly into one of our questions of how do you decide when to report the mean and the standard deviation versus a standard error in the mode or interquartile ratio? And I think we're going to talk about that a little bit more too.
Absolutely. But to give everyone a preface, so essentially you determine whether to report the mean and standard deviation versus median and interquartile range based on data normality. So if your data set is normally distributed, you would report the mean and the standard deviation. If it's not normally distributed, you would report the median and the interquartile range. So if without even testing, we can probably think that, looking at this data set, it's approximately normal. So we probably would report the average and the standard deviation for this data set. So that's how we would go about it. I will show you guys actually a formal way how to calculate that later. So no one's making guesses, but that's just so you guys have an idea of what that, what it comes down to. Does that make sense?
Yeah, very good explanation.
Awesome. Thank you so much. Okay, now let's go back to these slides. Okay, so one of the things I found in Excel was that, it's not as easy to calculate interquartile range as it is the other statistics. So I wanted to encourage you guys and also make you realize how easy some of this is. If you're conducting a really basic study and you do not want to pay a statistician and you're not going to use SPSS or R because it's just a basic study, you can definitely use online calculators. They make life so much more easier, possibly easier than Excel as well. So especially for calculating interquartile range, I've done this all the time. If I'm not doing a very stats heavy study, I will go and use the online calculator. I will copy and paste my data set right into the online calculator. This is one of my favorite ones, Calculator Soup. I can even share the link with you guys, and you just paste your data set, hit calculate, and it'll give you all the statistics. It gives you, your median, your min, your max, your IQR, your range, everything is ready made here. Now, one may argue this is not professional to report for publication purposes. Well, my counter would be that if you are conducting a basic stats study, which does not involve any advanced stats, in your methods section, you probably do not even have to report that what statistical software you use. You just say, we conducted descriptive statistics, simple as that, and ends it that way. Now, if you know how to use SPSS, etc., feel free to go ahead and do that. And that's something a little bit more professional to report. We will talk a little bit how to use SPSS a little bit further down in the series, but always feel free to use these calculators if you're just doing nothing more than descriptives. So let me just quickly do a quick example to show you what we find interquartile range using randomly generated data. So let's stop share. And I'm going to copy my randomly generated data from Excel. And I'm going to share my internet. Let's see, share. Okay, so I'm here on Calculator Soup. I'm going to copy and paste my data set that I just randomly generated from Excel. And I'm about to hit calculate. And as you can see, it nicely provides all the statistics you need. The first quartile, second quartile, third quartile, IQR. So if you're in a paper, if you're just looking to report the median and IQR, since your data is not normally distributed, look, your numbers are right here. However, this other data, it may look meaningless to you right now. But if you're trying to do something like a box and whisker plot, like this is all the data you need for that box and whisker plot to plot it. So actually using online calculators like could be sometimes easier than even Excel, and it could be quick to accomplish the purpose you want to accomplish. Okay, next I wanted to talk a little bit about confidence intervals. These are so important just because we see them reported in medical literature all the time. And, you know, in general, it could be just a very useful statistic to help you understand your data because it helps you generalize your sample data to the entire population. And what do I mean by that? Meaning, like, if you're doing a study on sickle cell disease, and you know what, you say, okay, I'm going to retrospectively review all the cases of sickle cell disease of patients that came to our ED in the last year. And you're just doing a study on these patients. Remember, this is like, even though you're looking at a whole year of patients, which may be like, 500 patients, although that's a large sample, it still is a sample. It's not all of the patients that showed up to your ED over the last 10 years. So confidence intervals are useful for any statistic because it helps you generalize that parameter that you have estimated from your sample to the entire population. In my sickle cell example, that will help you generalize what the what the actual value of that particular statistic would be if you were to look at all the cases that came to your ED in the past 20 years or in the lifetime of your ED. So they're actually very, very helpful for a reader. It also helps the reader understand how big your sample was. You will tend to find if your confidence intervals are very large, it simply means that your sample was very small, maybe like something like 10 or 25 charts. But if your sample size was very large, maybe 500 cases to 1,000, you would find that your confidence interval is very narrow, which is a good thing, right? Because it simply means that, the estimate of the parameter you're looking for, such as mean, median, et cetera, it's very close to what it would actually be if you were to look at all the cases and not just that sample. So actually sample size matters for that, and it's very important. Now, you do not want to, you want to have a large enough sample so that you have a confidence interval that you're comfortable with, but at the same time, not too large that you're going to exhaust yourself, that, you have to review a million charts. Like, I don't think a lot of us have the time for that, especially ED physicians. So you just want to find that balance between like having a large enough sample size, but at the same time, not a too small sample size. Otherwise, the CI becomes inconclusive. So in general, how do we interpret the CI? Technically CIs, we generally see in medical literature that 95% CIs are reported, and that's usually a generally accepted form. That's the number. I would not, encourage you to use anything except 95% confidence intervals, because even online calculators, everything is geared towards calculating 95% confidence intervals. So just to keep it simple, we want to stay that way. Otherwise, you can calculate it from scratch if there's a need be, but I wouldn't recommend that because it can get very time consuming and very messy. So in this example, you see I have here just to show you that, other size confidence intervals are used except for 95%, but we're going to stick to the 95%. And so how do we interpret a confidence interval? You generally see, like, as shown in this diagram, we have a lower bound here. So that probably that's our A and an upper bound here, that's a B. So intuitively, so your A is lower than your B. So, and your sample parameter is like somewhere in between, right? So say if the mean of your sample, is like 55 or something, like in our previous example, like that point would be directly in between this range. And the upper bound and the lower bound essentially tells you that, if we were to look at all of our ED cases, we are 95% confident the mean age of all those of sickle cell are between A and B. Like, it will not go beyond that range. So obviously it makes sense intuitively then that if we were to look at a larger number of cases, like A and B would be closer together because we'll be closer to the actual mean, the actual age. So again, where the confidence interval tells us if we were to look at all of the cases in this entire population, we are 95% confident that the true value of whatever we're looking at, the mean, median, mode, proportion, etc., would be between A and B. Okay, so that's that. Also, in terms of looking at, you've probably heard there's been a lot of arguments and a lot of debates under whether one should report, confidence intervals and p-values. And the reason why, I'm not going to get too into technicality, but I want to show you how, one can tell there's a statistically significant difference or not using a confidence interval. So if confidence intervals overlap, meaning that there is an overlap between the upper and lower bound. So I'll give you an example. Say our confidence interval for one sample was 1 to 20, and for sample B, in a different population, the confidence interval was from 15 through 30. Now we see there's some overlap between those confidence intervals, right? So there's an overlap of 15 to 20. So just for the fact that there's an overlap between confidence intervals, it simply means that there is no statistically significant difference between A and B. So that's one way to tell whether there's a difference or not. Now, if we had, again, sample A and B, but the upper bound, the lower bound for, sample A was 1 and the upper bound was 20. And for sample B, the lower bound was 30 and the upper bound was 50. Clearly, there's no overlap between those confidence intervals. So that simply means that there is a statistically significant difference between the parameters between those confidence intervals. Does that make sense? Are there any questions about that?
I think that's a great explanation. I think it's also something to kind of keep in mind of like, when we start talking about p-values, confidence intervals, we've moved away from it partly too because of like clinical significance too. Like we can have things that are significant with a p-value of less than 0.05, but doesn't necessarily always tell us that they're significantly different clinically, right? And so I think this is trying to help address some of that as well.
I completely agree, especially, with the p-value, this one always argues like, the cutoff we determine as humans, right? We determine that 0.05 is the cutoff or 0.1 is the cutoff. Oh, but with the confidence intervals, people are a little bit more confident in it just because, you have that lower bound and upper bound. So there's like some leeway to play with. So it makes people feel a little bit more comfortable about making their conclusions. Like the difference is large enough. They're very separate. All right. So I'm going to show you guys simply how to do a confidence interval on another online website. This is one of my favorites, vasarstats.net. So I am going to stop share for a minute here and then share the online calculator.
And Christine, while you're getting these up, how do you decide like what online calculators are reputable, like are okay to use in publishing versus maybe not so reputable? Because there's a lot of stuff out there that like you can pull off the internet that may or may not be correct, right?
Right, absolutely. So here's the thing. I'll just make a basic statement. So for basic stats, I would say that a majority of the online calculators are reputable. Like if a calculator can't tell you mean, median, and mode, there's like something wrong, right? But like if I was to do like, I would never do a regression or something using an online calculator. I would always use a legit stat software. Vasarstats, this again, I know is legit. This is something that I've been taught for my dissertation study, so I know it's valid. Another, like you should look for like cues, right? So I'm going to hit proportions and I'm going to hit the confidence interval of a proportion. Like, look for things like references, right? Look for references and look for like, cues that it's correct. Like this one, I know that there's been thought put into it because they're saying that the procedure is used by someone that has published on it. So you have to look for these online cues to kind of get it. But again, I would never use an online calculator for anything outside of basic stats. And if it's something basic as mean, median, or mode, like we all trust Excel. So we can use Excel. IQR, like I can play a little bit with the online calculator just because it's a basic stat. So that would be my 2 cents on that.
Thanks.
You're welcome. Vasarstats.net is one of my favorite for calculating confidence intervals. So again, I just clicked on proportions here. And then I'm going to click on the confidence interval of a proportion. So here, just refresher. So N is usually probably the total number of data points in your sample. So let's say something about like 400. And K is the number of things you are like, of interest. Like if it's binary data, yes, no, maybe 50 people responded yes out of 400 you surveyed. So I'm going to hit calculate. And then the proportion here is 12.5. And then we see 2 confidence intervals displayed here. A confidence interval without continuity correction and a confidence interval including continuity correction. Now, I don't want to get too into the weeds about this, but what I will tell you, and as you can see, they're generally about approximately the same, the lower limits and upper limits. But in general, you use no continuity correction when you have more than 2 categories. Like if our category, if we were looking at race, right? There's multiple races. There's Caucasian, there's Black, there's Asian, etc. Those are fields that have more categories, nominal data that have more than 2 variables. For those kinds of cases, you would use the confidence interval without continuity correction. For binary variables like yes, no, yeah, that's a good example of binary variable. Yes, no, any question that has only two responses, strictly two responses, those you would use the confidence interval with the continuity correction. So that's when you would do that. Are there any questions about that?
No, this is great.
Awesome. Thank you. All right. So next, we're going to talk a little bit about data visualizations. Now, I'm sure a lot of you have seen these things and they look really fancy in papers because people use all kinds of sophisticated software and stuff to do them. But at the end of the day, it's essentially the same thing, just created in a different software. So first thing, I think this is as complicated as it gets. We have our box plot. And if you recall a few slides ago, I shared that calculator soup calculator where I calculated interquartile range, and it literally gave you all the values for this, like minimum, maximum, interquartile range, quartile 1, quartile 3. Those are the values you literally would just plug in and draw your box plot. That's how simple it is. But you would never do this on your own. You just plug it into Excel or somewhere else, and they will do all the work with you. So box plot, just to explain what these things mean. They're generally used for continuous data. So only continuous data, you'll probably have a min, a max, a median, etc. So it's used for continuous data, and the end of this line represents a minimum, and left end of the line, and the right end of the line represents your maximum. Now, you've probably also seen these flipped, right? So if this line is more towards the bottom, that represents your minimum, and if it's on the top, that represents the maximum value of the data set. We have these little dots are our outliers. Your interquartile range is, essentially the two corners of the box. Your median is directly in the center of the box. Your interquartile range represents, your 25th percentile and your 75th percentile plotted together. Again, this is all calculated from your continuous data set. So this is very useful information to just kind of like help visualize what your entire data distribution looks like. And especially if you're comparing multiple different data sets, it will help the viewer to, look at box plots for every single data set you have if they're trying to compare, etc. So we can better understand the data distribution and like differences between means. All right, next we have a histogram. So histogram generally categorizes continuous data into evenly distributed bins. So you can see how many counts or the frequency of an occurrence within a specific range, right? So in this example, we have test grades. Obviously, the nice thing about this, even test grades can come into decimal places. So the nice thing about, histograms is that it allows you to nicely represent that. So we have about 10 students that have grades between 0 and 20. And this, includes all their decimal point grades, about, 20 students that have grades between 20 and 40, etc. So this is very useful for quantifying frequencies of data that can be, nicely represented into equal bins. So we can see here that, majority of students performed, scored between 60 and 80 on a test. This looks like, a college distribution clearly of great scores on a test. The histograms are very nicely for, portraying data of this nature. Compared to a bar graph doesn't usually use, bins to characterize data. Bar graphs are very nice for kind of, for more data that does not have decimal points or categorical data. Like if we wanted to nicely portray racial distribution or, favorite soccer teams, we would use a bar graph. And, each bar would represent, on the y-axis, the frequency of each type of thing we're measuring. And the x-axis would be each type of thing we're measuring. So, it could be a football team. It could be even if you're looking at Likert scale data, right? Each bar could represent 1, 2, 3, 4, 5. There's no decimal points in between. So that could be nicely represented on a bar graph. All right. So pie charts can be very effective if you're presenting something. Pie charts, again, are generally used for categorical data. To give you guys an example, if you conducted a survey of some type and you're trying to make a huge point that an overwhelming amount of people responded yes to a yes/no question on the survey, you would probably want to display that on a pie chart, right? Because each color represents a different category. And if your yes is blue and your no is pink, we'll see the pie chart dominated by yes if a majority of people responded yes. So it could be a very effective way of trying to make a point if you're trying to make a presentation. So you could use a pie chart or a bar graph interchangeably for categorical data, but I guess it depends more of the point you want to get across. Okay, lastly, for visualizations, I want to talk about scatter plots. So scatter plots are generally used to determine if there's visually determine if there might be a correlation or association between two continuous variables. Those are your X and Y variables. And, notice again how I use these terms. I introduced them at the beginning, but I use them over and over again. The idea of ordinal, nominal, or categorical, and scalar. Because again, different types of variables, they depend, the type of tests you use depend on it, as well as the type of visualization. Like, for example, you can't use, maybe a box and whisker plot for binary data. It's not going to be very effective. So just understanding the types of variables can help you navigate through some of these different things. So going back to scatter plots. So, X axis could be time. Your Y axis could be whatever measure height or something. As long as they're continuous variables, you can do a scatter plot. Scatter plots are very useful because just like our bell curve, although we're not quantifying what that relationship is, it'll just by plotting our data and looking at the data together, it can give us a lot of information, right? So if we want to see if two things are associated, two variables are associated, we just plot our X against our Y and just take a look at our graph. Clearly, in the first example, we plot our data points. If we're looking at time and height, we would see that, as time goes along, there's an increase in height. So that's a positive correlation without assigning any numerical coefficient to it, just by looking at it. On the next graph, we may see that, heights may decrease with time. So that's, an example of a negative correlation. Or if we just plot everything together and we notice that there's no association, which could be, common if you're just associating two random things and you don't expect to see one, that's also very possible. Now, in later PowerPoints, later tutorials, we'll talk about how to numerically quantify some of these associations, but a scatter plot is always a great place to start. Okay, so kind of tying this all together, we talked about a lot. We talked about different types of variables. We talked about different types of visualizations, different types of metrics you can use to report each type of distribution. And I'm sure you guys have heard of these terms a lot about parametric and non-parametric, normal and not normal. We even kind of talked a little bit about it at the beginning. But in medical literature, these terms become very important because a reviewer will come back and tell you that, no, you cannot use a t-test because this data does not appear to be normally distributed. And they haven't even seen the data. They just tell you that. And it's your job to either rebut them and say, no, I did a normality test, or it'll be like, oh no, I actually didn't check for normality. Because you'll see all these tests. You'll see Mann-Whitney U, you'll see Wilcoxon-Stein squared, and you're like, where do they get these things from? It's simply because the authors tested for data normality. And it's important to test for data normality because if you do provide the correct statistic according to normality, it makes your results more robust and more real and more presentable and believable. Otherwise, you might end up with a statistic that doesn't make sense, forget to the reviewer, and won't even make sense to you. So I'm going to tell you a little bit about how to determine whether data is parametric and non-parametric. And again, these terms are usually referred to data sets that are continuous data sets. We're not talking about binary here. And we're not talking about, well, actually, they could be used for both ordinal and continuous data because you can perform the appropriate tests on Likert scale data, for example, as well. So there's something, and this is a huge secret. People should take notes of this because if you ever get questioned about normality versus not normality, this is your answer to it. You say, I did the Shapiro-Wilks test and the data came back normal. So I was allowed to use the t-test. So I'm going to quickly show you how to do this. Again, Shapiro-Wilks test, this is easily available in SPSS, etc., and which I'll show you how to do it later, because if you're going to go to that extent to test for data normality, you probably don't want to use an online calculator because you're going to report using SPSS in your calculations anyway. But I'm going to show you how to do this quickly online. Okay, so stop share. I'm going to copy and paste my randomly generated data set from Excel, and I'm going to share my Shapiro-Wilks. Just a note, Shapiro-Wilks test can only be used for data sets whose, number of data points is less than In general, SPSS tells you 1,000. I would stick with that because that's more professional. Here saying it'll take a maximum of 5,000. And to be honest, I'm not sure if reviewers are going to point you out too much if you use Shapiro-Wilkes normality test or Kolmogorov-Smirov's. That's the other alternative. But they just want to know whether you did some normality calculation. So I'm going to copy and paste my data here. And I'm going to hit calculate. Okay. So Shapiro-Wilkes test, what it'll do is it'll give you a p-value. If that p-value is greater than 0.05, it means that your data set is approximately normal. And here it'll even tell you that your data is potentially symmetrical. And why it uses the word potentially symmetrical. As I said, in the real world, not all medians, and modes are going to be equal 100% of the time. They can probably be close together. Like one could be 20, the other one could be 21, the other one could be 22. That's probably close enough. But doing the Shapiro-Wilkes test will help you determine whether it's close enough. So that's the trick. This is a trick. So if this data set was something else, and I'll go back to my other screen, and it was the Shapiro-Wilkes calculator, it came back to, the result came back to something as non-parametric, it would look like this. My bad, that was also a symmetrical example. Oh no, 0.09 is still greater than 0.05. So bad example, but essentially, if that p-value was less than 0.05, your skewness shape, it would say potentially asymmetric. And essentially what that means is your data is not normally distributed, and you should use a non-parametric test for any calculations you would do. So what that essentially means is you would report medians instead of means. Parametric, you report means instead of medians. That's essentially what it means. And with the mean, you would report the standard deviation, and the median, you would report the interquartile range. So that at the very basic level, that's what it is. Now later in the future PowerPoints and webinars, when we start talking about statistical tests, we will have a lot more to put under each of these categories, right? Like for parametric data, you would use the student t-test to compare means. For non-parametric data, you'd use the Mann-Whitney U-test. So we'll keep on adding to this list as we start talking about more sophisticated tests, but this is just something to start with. Lane, do you want to say anything?
I think this is huge. The number of times I've been asked of like, are you sure you're reporting the right, I don't know, and I have to like defer to a biostatistician, or like you can look at your data and plot it right and say, oh, it looks kind of normal, but having a test that you can actually say for sure, and then being able to devise all your other downstream tests out of that is huge.
Yeah, I know that was really huge for me too. When I, when I learned about Shapiro-Wilkes, I'm like, yes, this is the key. This is it. There's no guessing anymore.
Online calculator is so easy to use. Like,
right.
It's like a no-brainer.
Yes, it's easy to use, no-brainer, and I do trust that one. Although I figure like it's really easy to do on SPSS as well, but I can show you guys how to do that later. All right,
and
awesome.
Just for the audience, like we are planning out, Christine is going to do a wonderful job. Like she's going to walk us through how to use some of these statistical software programs towards the end of the series. So it is coming.
Yes, absolutely. But yes, do not want to discourage you guys at all, especially if you're just doing a descriptive paper and you're not making any comparisons. Feel free to use the online calculators because I don't know how bad they can screw up with mean, median, and mode. Like I do not think. And like Vassar Stats, as you can see, could do a lot of these calculations and it's actually legit. It references, it tells you what methods it's used. So you can feel free to use that as well. Alrighty, so the last concept I want to discuss is p-value. P-value, as difficult as it sounds, and you've probably heard so many variations of this, it's not as, so let's say if we have a p-value of 0.67. What does that mean? It means that, if we were to repeat this data set, like, this analysis, that there's a 67% chance that your finding is not due to chance. So that means the finding is 60% probability that your finding is not due to chance. And 67% is pretty large. So that essentially means that, it's very likely that your finding is random and not, So if the p-value was less than 0.05, which is usually our cutoff point, like if it was 0.04, we would say that, there's a 4% chance that this finding is due to chance, which is very small. So that means it's likely that this finding is not due to chance, which makes it statistically significant. So that's why we say lower p-values mean statistical significance, simply because, it's less likely that that finding is due to chance. That's all it means. And here, you know, are our basic cutoffs, right? Because we represent it as probabilities. You know, the lower your p-value is, obviously, it's very strong evidence against the null hypothesis. So it's very likely that your finding is not due to chance. That's why there's these very, very low p-values, and there's these very, very high p-values. Obviously, if your p-value is 0.99, it's a very high likelihood that your finding was due to chance. Simple as that. All right. So in summary, what we talked about today, and the big thing at the top is the 3 types of variables, because I think it carried the whole conversation. And it's important for you to remember because it's going to carry this webinar. It's going to carry all the stats you decide to do in the future. There are 3 types of variables: continuous variables, nominal variables, or categorical variables, and ordinal variables. And depending on the type of variable you have, it helps determine what visualization to use, what test to use, etc. But, you know, you have our 3 types of descriptive statistics. We have central tendency, we have variability, and we have frequency distribution. You know, your basic central tendency statistics are mean, median, or mode. If they're placed on different pieces on your bell curve, it can help you determine whether the data is skewed or not. However, there's no need to guess that because you have your wonderful Shapiro-Wilks test to help you determine whether the data is skewed or not. So there's no need to overthink it too much. If you just want to see it, it's nice to see it, but that's what you have as your friend. Again, mean and standard deviation are reported for parametric or normal data. Median and interquartile range are reported for non-parametric data. Excel as well as online calculators can be very useful for calculating these. Excel is also very useful for visuals. I can actually show you. If you put a random data set into Excel, it will actually give you suggestions for what visuals to use. Let me just show you guys that really quick. And probably a lot of you know this, but I just probably need to show you for some of you that don't use Excel that often. So Excel has made it so nice. And, you know, this wasn't in previous years. And I feel like this was like 2016 or something update to the software. If you click data, what is it, data? Insert. And if you just select your data and click select recommended charts, it'll give you a bunch of options of how you could potentially represent your data. And some of these options will make sense and some of them will not make sense. You will make your decision on a few things. Number 1, Excel, I don't know how much it relies on artificial intelligence, but probably it's not thinking about whether your data is categorical or it's continuous or whatnot. So some of these are obviously going to make more sense than others. If you want to do something like a scatter plot or like this is what it'll look like. Again, it determines what your intent is and what type of variables you have. So Excel can be really helpful for just like shooting some ideas about you, about how you might represent your data. And it might help you determine it, but it's always good in the background to have an understanding about what types of data you're having and what is the message you're trying to communicate. And then, you know, after its recommendation, it has all charts and it'll give you the different options. Clearly, probably the pie chart doesn't make sense here. So definitely make use of these tools to kind of guide your way through the entire process.
Christine, this has been awesome. It's so helpful to go over the different types of variables and just like the core foundation stuff that I think some of us have taken for granted, is like just expected that you know, and never had someone sit down and just break it down for you. And like you said, it does kind of set the foundation for everything that's coming on later. So I'm really excited about this session. If there are any questions, I think I've interjected and put most of them as we were going, but if there are any additional questions, we're happy to have them. Just for reference, these are recorded and we will be posting them on the SAM website, and it should be a monthly series for a while until we get through a bunch of these basic core stats principles.
Thank you so much, Elaine. So I think we pretty much covered everything we had today. I just hit on my other point. And remember, your friend is the Shapiro-Wilks test for determining data normality. There's no need to guess, just use it. And that's your friend for the reviewer and everything. So that was pretty much it. Thank you again, Lane and Lynn, for us coming together and brainstorming and helping me make this happen. I really appreciate that. I think this is going to be really helpful to everyone. And it's just not, I think, having an interdisciplinary degree, so many specialties also struggle with this because they're not doing this on a day-to-day basis, right? They're doing their clinical work. So I think this is helpful to everybody. And as a junior researcher, if I can help you guys, I'm helping myself too. So thank you all. And I hope you got something out of this.
Thank you, everyone. We'll see you next month.